Okay, I'm going to do a really quick demo of my red-black tree programming language, I guess you could call it. So we're going to do this by manipulating image versus writing code, and the goal is to rebalance a red-black tree after an insert. So we've got the code primed here on the left. We've done the RB, we're implementing the RB insert method, and we've done a binary insert of the value, and we've colored the node red already. So now we have this RB tree representation where we have the top part of the tree, the node n, which is red, and then it has two children. And on this one here means that these two trees have a black height of 1. Black height is in the red-black tree terminology, all nodes should have the same black height. So if you have a sibling, right, you have to have the same black height as your sibling, right? So we actually, in this root tree construction here, we actually say, okay, the sibling of n has a black height of 1, if it exists at all. It could be empty. Okay, so we start off by saying, well, we want to solve a more general problem. We want to rebalance the tree when these are all k, because we're going to have to do a loop later. So we're going to change that to a k. So k is basically 1 at this point, and we can change all our 1s to k's. So now we have this tree of k height, n has a k, two children of k height, and a sibling of k height. Okay, so now we're going to expand our root here, right, the n's parent. And we're going to do that by clicking on the thing and dragging down. And it's going to give us 3 cases where n doesn't have a parent, it's empty, n has a black parent, or n has a red parent and a black grandparent. Okay, so we consider the case where n doesn't have a parent, it's the root of the tree, right? Then all we have to do is color n black, and we can turn that into a black tree. So we clicked on this thing here. Let me go and delete that really quick. Right, so we clicked on this little red dot here, and we've changed it into a black node, right? And then we click on the root here, which is empty, and we can say, well, now this is just its own red-black tree. So we could just compress that into its own red-black tree, right? Now we have just the tree and nothing else, completely proper, and then we can just return because we finished the rebalancing, right? Now the next case to consider is that we have a black parent. So if we have a black parent, right, then this tree is already perfectly balanced, right? So, this has k height, but this also has k height, so that's fine. And a black node can fold up into any kind of parent. So we can just go ahead and compress that directly, return. So this is the more complicated case where we have, the red parent and the black grandparent, right? So we just expand those both at the same time. Because if you have a red parent, any red node in a proper red-black tree is going to have a black parent. So we just take those two out at the same time, right? So now we have to sort of figure out how to rebalance. This is the complicated case. Okay, so the first thing we want to do is look at this k over here, right? Now these little black dots here on top of these little triangles mean that these are black node rooted, red-black subtrees. Right, but we don't know anything about this one because it's a black node, right? It could have either a red or a black node parent. So now we want to sort of expand that out and sort of explore multiple cases where we either have a black rooted subtree or a red rooted subtree, right? And if we have a black rooted subtree, right, this is sort of the more interesting case. Now we want to sort of rebalance these nodes up here, but we don't actually know the sort of the orientation, like is this k on the left or the right? We have these little star here that says, well, this could be flipped around or it might not be flipped around, right? So now we want to sort of compare these two, whether these are flipped around or not. So we can't do a proper rotation until we know if we're, the proper left-right bearing. So now we basically drag here, we drag this sort of, we call this an axis variable over here to this axis variable. And it says, well, now these are both the same. They're both alpha. So if they're both the same, right, we don't exactly know if they're left or right, but we know that both are either left or both are either right, right? So we could sort of look at it like this, or we could flip it around and look at it like that, right? So now we can just rotate. Now we can actually do our rotation up. We do our rotation. We rotate P above G, right, the grandparent, right? And then Now we can just sort of recolor these, make this black, make this red. Now we have k plus 1 with a k plus 1 sibling, and so this tree can be compressed. We're done. Now this is the other case, where they weren't the same, where they were different, right? If we signify different, we still put the alpha in there, but we just flip the left and right child of p. And now we just have to do just one more rotation, right? But it's interesting because now we've done another rotation. We've rotated n up above p, right? But if we look at here, right, it looks just the same. It's just p and n are swapped, right? And because these states are the same, we can do a goto statement. So basically goto says, well, there's already a state in this program that matches the state that you just computed. So let's just go there and then reuse the logic from that point. So we go from here up into the other case, which had the same shape. Right, now we have only one more case to consider, which is where the tree up here, let's see, it has is rooted by a red node, right? And we call it U. And so, if you go cheat and look on Wikipedia, it says, well, the best way to handle this case is to loop. Start over again and just work your way up the tree, right? But first we have to sort of color G red, P black, and U black, right? Now and then also we have to compress these trees. Sorry. Right now, if you look at it, this shape here that we just computed, right, looks just like up here after we did the k, after we assigned the k, right? It's just that instead of having k, we have k plus 1 now, right? Which means we can go to that state over here. So we do a go to up here where we began, just sort of the head of the loop to say. And then also we've done this reassignment of, well, now k is k plus 1 and n is g when we go up here and redo the code. And that's it. We're done. So now we've implemented a complete balancing routine for a red-black tree. Thank you.